So, hello everyone. Today we are going to be talking about electric field due to a ring, a disk, and then an infinite sheet. So, first let's talk about electric field due to a ring. So, as you can see, I have taken an electric field with charge q and radius r. Now, in order to find the electric field due to an object like a ring, we can consider the ring to be made out of several small charged particles like dq, and several like an infinite number of dqs can be arranged in the form of a ring to form a charged ring. So in order to find the electric field, what we can do is we can basically calculate all the individual electric fields produced by the small dq over here, and then we can integrate it to get the net electric field. So as you can see, the electric field that dq produces is given by k multiplied by dq divided by s square, which is basically the distance between dq and the point in which you would like to measure the electric field. Now we basically have a point P here, which is a distance L from the center of the ring, which is basically the distance on the axis of the ring. So what we can do is basically calculate the distance, which is S, from dq all the way to P, and then we can substitute in this formula, and then we can integrate it like this to get the field. Now you might wonder what this cos theta here is. So if you actually look at the electric field, it's going to be in this direction, and it's going to be made out of paths in the x-axis and then the y-axis. Now if you look at the ring closely, you might observe that all the forces on the y-axis, which is here, would actually get cancelled out as it's symmetric. So basically the y component that this dq creates would be cancelled by the dq, which is over here. If we take this as a dq, it's basically gonna produce a field that's equal in magnitude and opposite in direction, and they are gonna cancel each other out. So we can basically ignore this e sin theta. I mean, we only have to add up the e cos thetas, so that's why there's a cos theta over here. Now while integrating it, we can actually remove all the constant terms. Now if you observe, the constant terms are k, cos theta, and s square, which is basically this hypotenuse distance. This is actually a right triangle, so we can take this as a hypotenuse, which is basically r square plus l square equal to x, as this is r and this is l. Now as you can see, the integral of dq is basically just q, so we arrive at this formula over here. Now s square, as I said before, is r square plus l square, so we can take that and substitute it here, and then we would get r square plus l square, and we can rewrite cos theta as basically now this theta, right, this theta and this theta are going to be equal, so we can basically write cos theta as adjacent side, which is this l over here, divided by the hypotenuse, which is this s over here. So it's going to be l divided by this root of r square plus l square, which is s. Okay, so now we can multiply them, and then if you combine the denominator terms and the numerator terms, you are going to get this equation over here. This is basically the field due to a ring, where this is the L is the distance of the point from the center of the ring, and this r is going to be the radius of the ring, and this q is going to be the charge of the ring, and then this k is basically the constant. So now to find the electric field at a distance L from the center at point P over here, we can basically instead, as you know, we took dq as a point charge here, we can basically take dq as a small circle over here, or a small ring over here, and as we have already calculated the electric field due to a ring, we can basically put the same equation here for dq, as we have taken the ring that's being formed over here as dq, and it's going to have a width of dr, and this disk is actually going to have a charge of plus q and radius r. So now if you integrate this, you can basically now before you actually integrate this, you need to convert this dq into dr. As you know, we are integrating with respect to this r over here. As you know, this is going to be 0, and then we slowly increase the radius all the way to r. This is going to be 0, and then this is going to be r. We basically slowly increase the radius of the ring, and then we add all the fields generated by all the rings to get the net electric field. So in order to convert this dq to dr, you can take this equation over here. Sigma multiplied by pi r square is equal to q. As you know, sigma is just total charge divided by the total area So as you can see, we can differentiate this, and if you differentiate it, you are gonna get a dq and then a dr. Now we can substitute this whole bit in the place of dq. So once you substitute it in the place of dq, you're gonna get this equation over here. Now as you can see, we can remove all the constant terms, which is basically k, l, sigma, 2, pi, and that's it. So we can basically remove these things, and we're gonna end up with r by r square plus l square whole cube by and whole cube, and then you take a root and then multiplied by dr. So now in order to integrate this, we can actually use the u substitution method, and I've taken u as this part over here. That's going to be our u, which is r square plus l square. So now if I differentiate u, I'm going to end up with 2r into dr. So now I need to substitute this. I need to modify the equation in order to put this u over here in the first equation. So I can basically multiply and divide by 2. I can multiply both the numerator and the denominator by 2. So if I do that, this whole term over here is gonna basically be du, and you can, as you can see, I've put du here, and then this whole term is just gonna be u, and this 2 is just gonna be put right here. You can't really do anything with it right now. So once you integrate it, it's basically gonna be you add 1 to the numerator, and then you take that and then you put that in the denominator as well. So once you do that, you're gonna end up with 1 by 2, which is basically this 2 multiplied by negative 2, and you're gonna get and multiply that by 1 by root u. And as you can see, I have substituted my u here, as u is equal to r square plus l square. I have put that equation back here. So now what you have to do is basically subtract. You have to input the higher value into this equation over here, and then you have to subtract it by inputting the lower value into the equation as well. So you're gonna basically do it like this, where in place of r, as you can see, first I've substituted r, and then in place of r in the second equation, I've actually substituted 0, which is going to result in root of l square, and that's a negative sign on the outside. As you can see, there's a negative sign here and there's a negative sign here. We can basically bring it inside to make it simpler, and I've substituted this equation back here into the original one, as you can see. Now here, in order to simplify this equation further, you can actually bring this L to the inside. As you can see, this L will cancel out with this L, and then you're gonna end up with another L over here. And you can basically write K as 1 by 4 pi epsilon, and you can cancel this 2 pi and this 4 pi, and then you're gonna end up with the 1 minus L by root of L square plus R square. Now as you can see, after a simplification, I have ended up with this equation over here. Now sigma here is basically the charge density, right? So it's q by pi r square. So now we can actually use this formula in order to determine the field that has been created by an infinite sheet. Now you can basically, instead of imagining the infinite sheet as like an infinitely big square sheet, you can also imagine it like a infinitely big disk, right, with like a radius that's infinitely long. So we can use this exact equation over here, but this time, as it's an infinite sheet, it's gonna have the radius equal to infinity. So we just have to take the limit of r tending to infinity. So basically, if I take r square out of this bit here, I'm gonna end up with this equation. As you know, infinity, the a finite value divided by an infinite value is 0, so this is going to tend to 0, and if that tends to 0, this whole thing, this whole equation, we can just ignore it, as it's going to be 1, and this is also going to be infinity, and this is a finite value, therefore this is also going to tend to 0. Now if that tends to 0, we're only going to be left with this term over here, as 1 minus 0 is 1, and you multiply by 1 and you're going to get the same thing. So the net electric field is going to be sigma divided by epsilon naught, which is basically the charge density. Now for infinite sheets, they would actually give this charge density in the question, so you don't have to worry about calculating it, as it's impossible to calculate it, as the sheet is infinite. It's gonna have a total charge that's going to be infinity. As you can see, there is no L term here, so this L term is actually we can't find it here. It's gonna be independent of L, so no matter at what distance you consider the point, it's always gonna result in the same field. So this was my short presentation on electric fields due to ring, disk, and infinite sheet. I thank you for watching this video. Bye.